Okay, so the final thing I want to do is look at the image that's going to be produced by this lens, but instead of putting the object out here, I'm going to put the object inside the focal length. And you'll see why that ends up being quite interesting in a moment. So I'm going to kind of move this to the side. We've got one last little drawing here. And so we're going to, again, we know from our workup in this first case that we end up with a focal point on either side here. I'm just going to center this on 15, so we end up with a focal point here 3 centimeters away. Here's our F value, and 3 centimeters away here on this side. So we've got a focal point here. Okay, so this is characteristic of the lens that we are working with. And then we're going to put an object, let's put it inside the focal point. And so we can put the object, let's say, 1 centimeter away from the middle of the lens. Okay, so I'm going to put it right here, let's say. And I'm going to do what I did before, where it's going to be 2 centimeters high. Okay. And this tree is about 2 centimeters high or thereabouts, and it is at a very tight distance. It's going to be 1 centimeter from the lens. So this is our S, our distance to the object, and that's 1.0 centimeters. Okay. Now, how do we do the ray tracing in this case, and how is it going to be different? Well, the first thing I'm going to do is the first thing I did before. I'm going to send a ray from the very top, parallel to the axis, right to the center of the lens. So straight from the top into the lens, and as before, we know just by definition of how this lens behaves that it's going to pass through the focal point. There's no mysteries or differences quite yet. Okay, well, the next thing that we can do is we're going to draw a ray from the top straight through the middle, because we know that one is not going to refract. That's an easy one to draw. Okay, I'm going to draw that straight through, and here we go. Now, at this point, we're starting to get a sense that this isn't going to work quite as well as we may have wanted, because these two rays are diverging, which means they're not going to converge to a point. So if they don't converge to a point, we're not going to get an image over here. And we have one more line that we could draw, but it's a little bit tricky, and that is we could, again, thinking about ray reversibility, where would the ray be if it's going to go from the top of the object, but through this focal point? Of course, we're talking more about, again, the ray moving to this side, to the right. But I don't want to line this up improperly, so I'm going to align it with the focal point here. So that's going to go up here, still going in that direction, and it will be parallel to the axis that we drew. Okay, so now we've got 3 rays that are tracing out the behavior of the lens and looking for where it's going to produce an image. It does not produce an image over here, that's clear. But what we do in this case is we're going to trace back where these rays are going to converge on this side. So we're going to draw this in dotted lines, tracing this one back, and then I'm going to trace this one back. and I'm going to trace this top one back. Okay, and what we see is we get convergence at this point. So I'm just going to draw this down to the axes and make a little measurement here of, okay, how far away is that from the middle of the lens? Well, in this case, it's looking like, well, we're going to center it on something easy, 20. So we're going to go 1.5, so it's about 1.5 centimeters, about 1.5 centimeters away. Okay, so we're just going to note that down here. So we're going to draw out S primed. S primed is equal to about 1.5 centimeters. And hey, I might as well just make this into an image here, this tree. Okay. And we can also get a sense of, well, how big is it? Well, it's about 1, 2, 2.5, let's see, 2.75, we'll just kind of call it 2.8. So we've got an approximate H prime of let's say about 2.8 centimeters. Okay, so in this case, we produce a virtual image. This is a virtual image. On this side. And that happens whenever you have the object inside the focal length of the lens. Now, as before, we could do a calculation to get a more exact number so that we get a sense of, well, how good were we in very carefully drawing this all out. And so we can do this just as we did before. I guess I'll draw it over here. And we're going to apply our thin lens equation again. So I'm just going to jump right to the S prime part of this. So S prime is equal to S F over S minus F. Okay. And so we have, in this case, we've got 1 centimeter and 3 centimeter for our focal length, and then we've got 1 centimeter minus 3 centimeters, and so we get this S primed of this is going to be 3 over 2 centimeters, or sorry, 1 is negative, so negative 1.5 centimeters. Okay, so the negative here just means that it's on the same side as the original object. So the negative means the image is on the same side as the object. Okay. Now the other part that we could do here is the magnification. So we could say, well, our magnification is minus S primed over S. And so that's going to be negative, and then negative 1.5 centimeters over, it was 1 centimeter. And so we get a magnification factor of 1.5. So that means it's going to be bigger, and we saw that. Okay, I don't have room here to do the actual height, but I can do that over here. So we can say, well, our H primed here is going to be our absolute value of the magnification factor times the original height, And so this is going to be 1.5 times our original height, which was 2 centimeters. And so we get a resulting height of 3 centimeters. Okay, so in this case, we were bang on with our position, but we were a little off on the height, and it was just a little crowded. That's why I think that was a little off, but it was pretty close considering, you know, that this was straight off just drawing all of this out. And the other thing to note here is that we also saw in the magnification factor that it was positive, so it was upright. So we got the orientation, we got the magnification, and we got the position in 2 different ways. We got them using the thin lens equation and the magnification equation, but we also got them from just drawing everything out. So that's our convex lens.